Hello, good morning. So today is the second day of this course. So in the last class, if you remember, we talked about the symmetry aspect of different objects and different molecules. I showed you quite a number of structures of different objects as well as certain molecules, and we discussed about the symmetry aspects of those, and we said that okay, some molecules are more symmetric than others, and ultimately we also showed that there exists something called symmetry element and symmetry operation, which is like symmetry operation is the a movement of a body by which you end up having an indistinguishable structure. And today what we are going to do, we want to find out about the symmetry elements and symmetry operations in a bit more detail. Okay, so what are the symmetry elements and symmetry operations that a molecule can have? Okay, so one can have 5 different symmetry elements, and we can generate several symmetry operations out of those elements. Okay, we will look at that in greater detail. So let's look at one by one. So as you can see on the screen, that you can have an element called identity, another element called proper axis of rotation, and you can have mirror planes, you can have center of symmetry, and you can have improper axis of rotation. So now let's look at one by one what is what. First, let's look at the identity the element of identity. So what is it? So before going to the details of this identity operation and all these things, let us also see what this identity operation is denoted as. Identity operation, this is denoted as E. Okay. Now, what is this identity operation? Before going into the molecular structure, I will give you a very simple representation of this identity operation. Suppose a person is looking at a particular direction, then he can take several turns. So one can take a complete right turn, that is by 90 degrees. So if I take a right turn, I will be looking at this direction, and then if I take another right turn, then I will look at the back, that is toward the board, and then 2 more right turns, I'll be coming here. So there is a very nice story about an United States Army drills. So in Army drill, what you have is a commander will tell you to take a particular position. They call it take a face. So a commander will take right face, left face. So you move by rotate by 90 degree, either on the right side and left side. So there is another turn, that is by 180 degree. You actually take an about turn. So this is called an about turn. Now the commander says take an about turn, and then it takes one more about turn. Now sometime in the drill, the veterans, the aged person who has retired from army, they come and take part in the drill. So one of the veteran, he was taking part in the drill, and then when he heard the about turn command, he starts turning around by 180 degree. While taking this turn, he realizes that he is old enough and it's very difficult for him to take the turn in a proper way. He is twisting his leg and all these things. And he knew that the commander will ask him to turn around again. So he has to take 2 about turns. So he realizes that, well, ultimately I will be looking at the commander at the end after taking 2 about turns. So if I do nothing, then also I am having the same position. So this idea of do nothing is actually an identity operation. So if you look at this picture here, the person is looking at us, and then it keeps on taking turn from here to here, and then here to here, and then here to here, and then here. So ultimately there is no change in the position of the person. So now if I do not go through all these intermediate steps, and if I come from this state to this state directly, the symmetry operation that we have performed is an identity operation. Okay. So essentially you can figure out the identity operation means you do nothing. You keep an object as such in its position, you get obviously the identical structure because you have not done anything. So this identity operation is also called do nothing operation. Okay. And this is the easiest thing. And no matter what, any object in this universe will have at least one symmetry element in it, and that is this identity element. Okay. So anyone can do an identity operation on any object and get an identical structure. Here it's identical, not only indistinguishable. Okay. So that is about the identity operation E. Next, we talk about rotational symmetry element. Okay. Or this is also called proper axis of rotation. Why it is called proper, we will talk about this during this course, but let's for the time being just call it as a proper axis of rotation. So in the last class I showed you an example of rotating an equilateral triangle by 120 degree and getting that indistinguishable structures. So that particular axis is called axis of proper rotation. Okay. And this axis of proper rotation, this symmetry element is designated by this Cn, C subscript n. Now in that particular example that I gave you in the last class, we had an 120 degree rotation about that particular axis which is perpendicular to the triangle. So what is this n? Okay. So you can see that for Cn, n equals to 2, we have an 180 degree rotation. If I have an 120 degree rotation and we can get an indistinguishable object, then the order of this rotation, this n here that is written in this Cn is called the order of rotation. Okay. So for an 120 degree rotation, you have an order equals to 3. Similarly, for a 90 degree rotation, you can have an order 4. So you can easily figure out that if you have, say, an object like a square, a perfect square, you can imagine an axis through this point, and this axis is perpendicular to this plane of the board, then for every 90 degree rotation you get an indistinguishable structure, because this, if I mark 1, 2, 3, 4, now you can easily do, because you have already seen it for the triangular case, you have another square, because square is not going to be changed to a triangle, right? Square will remain a square. So when you give a 90 degree rotation, so 1 will come here, 2 will go here, 3 will go here, and 4 will go here. So ultimately what you have is this 1, 2, 3, 4. Until and unless you have these numbers, you have an indistinguishable structure, that is a square. And this is done by a rotation by 90 degree. Okay. So this axis, this Cn here is known as C4, and 4 comes from this relation where your n is equal to 360 degree by the angle of rotation, right. So 300 here, it is, this rotation is about 90 degree, so the angle will be 360 degrees by 90 degrees equals to 4. So I have an axis C4. So, in that way, if I have a rotation of 60 degree, 30 degrees, I can find out what is the order of rotation and the name of the particular rotational symmetry, that is C10, C8, C6, whatever. Okay. For a 60 degree rotation, for example, it will be C6 because 360 degree by 60 degree, right. So it will be C6. Now, you can see that I can vary the value of n. I can go from, say, like C3, 4, 5, 6. So I have not written there C1. Why not? Because C1 will mean what? C1 will mean, from this particular relation, it will mean that n for C1, n equals to 1. So n equals to 1 means I must have a situation where this angle of rotation is equals to 360 degrees. This is exactly the case what we described just some time back when we were discussing about the identity operation, right? So that's why C1 is not mentioned anywhere, because C1 and E are the same. Okay, so we have seen that, okay, n can be like 2, 3, 4, 5, 6, 7, 8, depending on the structure of the object or structure of the molecule in particular. So like for benzene I have, so C6, right? So benzene structure is like this. So this position of the carbon atoms and the associated hydrogens, and if I assume equal distribution of the pi cloud, then I can have an equivalent or indistinguishable structure for every 60 degree rotation about the axis which passes through this one, right? So every 60 degree I can have the indistinguishable structure, and we can have for this one an axis C6, and this particular axis is C6, right? Now, in that way I can go increasing. So can I have something which is C infinity? That's the question, right? So from this expression it looks like, yes, I can have. What is the what is the solution? That means here I have to have n equals to infinity, right? So if I equate this one to be infinity, what do I have here? I have extremely large number, right? Almost like an infinity. So in that case, what I have a situation like an object or a molecule which has an axis about which I can give any turn by any amount of angle, and I can get an indistinguishable structure. You need an example, right? So here is one example for you. Carbon dioxide. Now look at the axis. If I have an axis passing through all these atoms, right? This is a linear molecule, right? Carbon dioxide is a linear molecule. And if I have an axis passing through this linear molecule, through all the atoms, then you see about this axis all around, this is highly symmetric, right? So it doesn't matter whatever be the angle by which I rotate, it gives an indistinguishable structure. So in a sense, I can give an infinite amount of rotation before it comes back to its original configuration, correct. So because I can give this infinite degrees of rotation about this axis and get indistinguishable structure, this axis is known as C infinity. Okay. Now we said that this operation is called rotation, and really we should say it's a proper rotation. Why it is proper? Because if I really can have an axis that will change this molecular configuration from one to another indistinguishable one. Okay, so there can be really an axis there. So that means that there will be something which is not like this, that is not a proper, rather improper. Okay, we will come to that. It is there, and we will come to that. Now let's see some more example of this rotation. So as I said that we can have C2, C3, so C4 and so on. So here is an example which shows you a two-fold rotation, okay, and the axis about which this two-fold rotation is taken place is called two-fold axis of rotation. So here we have a molecule H2O, okay. So if I have an axis which bisects the angle HOH, then we can rotate the molecule about that axis, right? It is given here, okay. So this is that axis about which you can turn them. So you see we get an indistinguishable structure by a rotation of 120 degree, and another rotation by 120 degree will end up having the same structure back. Okay, so this is an example of C2. Okay, now let's come to threefold axis of rotation, which we have already looked at in terms of ammonia. This is another example, which is boron trifluoride. So here you can see that one fluorine is marked by a different color than other fluorine, so that you can actually distinguish them. Okay, so now by 120 degree rotation you get an indistinguishable structure, but you can actually distinguish still because you have colored one of them separately, but in a its chemistry is not going to change because BF3 is still BF3 there. Okay, so you can give more rotation and you can change the positions of the fluorine atoms, but they remain indistinguishable. Though because of the color you can distinguish them here, at least on the pen and paper. Now we have been talking about only one particular axis about which I can have a proper axis of rotation. Now it's not necessary that in a particular molecule we have only one type of axis of rotation. Okay, so here is one example when you talk about a trigonal planar molecule. Okay, so say this is a boron trifluoride. Okay, so all the atoms are in the same plane, so it's a trigonal planar. Now in the last page we have seen that there is a C3 axis, right, about which you can have 120 degree rotation and you can get the identical structure. But is that all? No. Here you see that I can imagine an axis which is right here, which passes through one fluorine and one boron. That particular axis you can have an 120 degree rotation about that particular axis, so you can get an indistinguishable structure. So you have three boron fluoride bond, right? So this is 1 and this is 2 and this is 3. So you can have the same type of axis, same type of C2 axis through each of these boron fluoride bonds. So you can essentially have 3 C2 axis for this molecule, and you can have 1 C3 axis. Okay, now we'll also see that this C3 is an element Now when you operate this C3 consecutively, you can get indistinguishable structures. So you can have C3 followed by another C3 and then another C3, and you can keep going until unless you get an identical structure. So if you do 2 successive C3s, then you have something called C3 square. We will talk about these things much later. And similarly, you add one more C3 into this, and you can have C3 3, which again is nothing but the identity operation, right? We have already discussed that. So in this particular case, what we learned is that a molecule may have more than one type of proper axis of rotation, and here particularly we see that the molecule has C3 as well as C2, and it's also not necessary that this C3 and C2, that is 2 different axes of symmetry, they will be coinciding. Okay, so they can have they can be at different plane and different directions. Okay, or you can have the 2 different axes in the same coinciding together. Okay. So before going to the next one, let me also clarify the last point that I made. That is, in the case of BF3, we saw that C3 and C2, they are not coinciding, but in certain molecules you can have more than one proper axis of symmetry coinciding together. Okay. So for example, you can have let's take this particular molecule, benzene here. Okay. So we have seen that there is an axis about which you can give a 60-degree rotation, and you can have a C6 axis. Now for every C6 turn, this hydrogen goes here, this hydrogen goes here. So you give a 60-degree movement here. Now if you want, you can have an axis here, and you can rotate in such a way that this H comes here. That is, I can have an 180-degree rotation, right? So this 180-degree rotation about this axis without going through this. So directly you rotate and bring it here. Do not stop here. So this is a C2 axis, right? So C2 and C6, they are about the same axis. Okay. So which is different from B3. But again here, this is not all. You can have many other rotational axes. For example, what you can see here, that is about this, you have a C6 axis, you have C2 axis, okay, and you can come from here to here directly, and then from here to here and here to here by 120-degree rotation. So thereby you have C3 axis. So all these C6, C2, C3, they coincide on each other. Okay, they are about the same physical axis, if you can imagine one here. But there are other axes, like if you connect this hydrogen to this hydrogen, you find a symmetry axis here, about which if you give a rotation of 180 degrees, you will find an identical structure, because this will come here and this will go here. So it is just a flipping. So similarly, this will do the same job, this will also do the same job. Okay, and if I can imagine an axis like this, this will also do the same job. Okay, so I can have 6 different C2 axes which are lying on the plane of the molecule, not coinciding with this C6 or C3 or C2, and this C2 is different than the C2s that I just showed you. Okay. Now let's move on to the next symmetry element, which is known as a plane of symmetry. Okay. So what is this plane of symmetry operation? Okay. So, you imagine any object or any space, if you take this xyz coordinate and you reflect it about a plane, and if you get an identical structure that is having coordinate minus x, minus y, minus z, okay, then you get equivalent and you get a rather indistinguishable structure by this reflection. So, you are doing a reflection about a plane and you are getting indistinguishable structure, and this plane is a symmetry plane, okay, and this symmetry operation is called plane of symmetry, okay, or also sometimes called reflection operation, okay. Now, this reflection operation is or the mirror planes, they are denoted by a symbol sigma, okay. So, all the plane of symmetries are denoted by the symbol sigma. Now, there can be a different type of sigmas. So, you can see that we have something special called sigma h, sigma subscript h. So, sigma h is a mirror plane which is perpendicular to the principal axis of rotation, okay. Now, you also have something called sigma v. Sigma v is also mirror plane, but this particular mirror plane has a particular characteristics which says that this particular mirror plane will contain principal axis of rotation. There is another type of mirror plane which is known as sigma d. So, sigma d is a mirror plane that bisects the dihedral angle made by the principal axis of rotation and two adjacent C2 axis. Here one note is that this 2 is actually a subscript, okay. So, this mirror plane bisects the dihedral angle made by the principal axis of rotation and two adjacent C2 axes which are perpendicular to the principal rotation axis. So, you can see that whatever be the name sigma v, sigma d or sigma h, their functions are same, okay. So, this subscripts v, d and h just are used to separate different planes of symmetries, but their jobs are same, okay. So, in the following class we will talk about more about this mirror planes, and we will cite some examples and go to the other kind of symmetry elements and symmetry operations, okay. So, see you again in the next class. Thank you very much.